Hello, welcome to another module in this massive open online course on applied linear algebra. Let us start looking at another very important concept which is based on principles of linear algebra, heavily uses linear algebra, and that is the concept of LMMSE estimation, which is a specific case of MMSE estimation, but LMMSE estimation is more popular in general owing to its tractability and easy applicability, right, low complexity, and naturally LMMSE, as the name implies, linear minimum mean squared error estimation, is used in the analysis of linear systems and essentially linear models, right. So, let us look at the concept of LMMSE, which is essentially stands for, I am going to explain the name in detail, linear minimum mean square. Mean square, or you can also say mean squared error. This is the principle, and the key word here is linear. This is linear in nature, all right. So, this estimator is linear in nature, right. And the idea here is the follows. So, given like y bar, this you can think of this as the observation, right, given y bar, which is the observation, which is essentially a random vector, right. Which is y bar, which is the observation, which is a random vector. The task is to estimate another vector x bar, right, which is also basically a random vector, right. This is also random, that is x bar essentially is an underlying vector, right, which drives the model, all right. You can think of this as an input to a model, and the output or the observation is y bar, and therefore, naturally we would like to use y bar, which is essentially the y, we would like to use y bar and determine what is the input x bar that drives this model, right. So, essentially if you look at this as an input output system, right, for example, this is your system, which by the way need not necessarily be linear, okay, not necessarily linear. The system itself is not necessarily, what is linear is the estimator, that is the interesting. So, even though the system is not necessarily linear, one can construct a linear estimator. It might be suboptimal, but we will be interested in finding the best linear estimator, right. So, that is the point. So, here you have the input, which is x bar, which is driving the system, and this is your output y bar. And now you want to use y bar to estimate, you use y bar to essentially estimate what is the input x bar which is driving the model, right. This is essentially driving your IO model. this is the input to the model. Okay. And the point here is what we want to exploit is the fact that x bar comma y bar these are correlated. This is a very important point. X bar influences y bar. So, naturally x bar and y bar are correlated. We want to exploit this correlation, right. We want to exploit the correlation between x bar and y bar to determine x bar from y bar, that is the point. So, exploit the correlation to estimate, that is the important point here. Exploit, which is a very important aspect of MMSE estimation, is exploit this correlation to determine x bar from y bar. Now, let us look at the properties of x bar and y bar. For simplicity, let us assume that expected value of x bar equal to 0, expected value of y bar equal to 0. This is need not be the case, but this principle can be readily extended to scenarios where they are not 0 mean. For simplicity of analysis, let us assume that these are 0 mean. I will talk to you about what to do when these are not necessarily 0 mean. And then what happens here is your expected value of, now we are interested in what are known as the second order statistical properties. When we talk about that, we have expected value of x bar transpose, which is Rxx. This is the covariance of x. Then we have expected value of y bar transpose, which is RYY, which is essentially the covariance. This is also something that you must be familiar with. This is the covariance and expected, the interesting quantities are expected x bar y bar transpose, which we denote by Rxy, and expected y bar x bar transpose, which is Ryx. And these are essentially what the interesting quantities, these are what we call as the cross covariance. In fact, these cross covariance matrices, these are what are capturing the correlation between x and y. If these cross covariances are 0, then naturally it means that x bar and y bar are uncorrelated. If they are uncorrelated, then there is not much you can do about it. Obviously, it makes sense if x bar and y bar are not correlated, right, then it is reasonably difficult. And you can see if there is no correlation, one cannot expect to determine or get an idea of x bar from y bar. The better the correlation, the better is your estimate of x bar based on y bar going to be, right. So, that is a very intuitive idea, right. So, cross covariance, and this basically captures the correlation. This captures the correlation between x bar and y bar, that is the interesting aspect. And we can also see that Rxy, this is nothing but these are the transpose of each other, right. So, this is essentially what you can see is that Rxy equals, this satisfies the property Rxy equals Ryx transpose. So, that is, these are basically the different quantities that we are going to use and now we are going to estimate x hat as the following thing. X hat, let us further assume that just to give these dimensions, let us assume that for instance y bar, this is an m cross 1 vector, all right. This is an m cross 1 vector, m cross 1, and x bar, this is an n cross 1 vector. Okay. X bar, this is an n cross 1 vector. Okay. Now, the idea here is to determine the estimate x hat equals C times y bar, where naturally this matrix C, this is going to be an n cross n matrix, because this is n cross 1, this I am sorry, this is m cross 1 and this is your n cross 1, all right. So, this is going to be an n cross m matrix, and essentially you can see this is a linear transform, right. So, this is a linear transform of y bar implies this is a linear estimator. Okay. So, that is an important point, implies this is a linear estimator. Okay. This is a linear transform of y bar, implies this is a linear estimator, and hence the LMMSE estimate. Now, let us look at what is the LMMSE. What do we mean by the LMMSE? So, there are a couple of terms. One is linear minimum mean square, and this is estimator. Now, let us understand. So, this is basically the anatomy of this term. Let us dissect this term and understand the meaning of each component in this. This is a loaded term, LMMSE, right. The first thing to perform LMMSE estimation is to essentially understand what this represents, all right. So, we have the vector x bar and we have the estimate x, okay, which is essentially a linear estimate. Okay, that is, so that explains part of this. So, that explains the linear and estimator. Minimum mean square error, I am sorry, this has to be error. Okay, linear minimum mean square error estimator, that is your LMMSE estimator. Okay. Now, so now we need to find the error between these, the estimator and the actual quantity. So, this basically is the error. Okay. And now, we take the square of this error, you take the norm. So, this is where you get the squared error, and now you take the mean of this squared error. Now, you take the mean of this squared error, all right. So, we are performing the mean of the squared error. the mean of the squared error, and then we want to find the estimate x hat such that we want to minimize. So, this gives you the minimum, right. So, this is essentially your linear minimum mean squared error, that is basically find the linear estimator x hat equals C y bar such that if you look at the square of the error norm x hat minus x bar square, and you look at the mean, that is expected value of norm of x hat minus x bar square, that should be minimized. That is what your linear minimum mean squared error estimator is doing. Now, the condition here is that x hat, important condition here is that x hat equals C y bar, that is x hat, this is essentially a linear estimator. Okay. X hat is constrained to be x hat is constrained to be a linear estimator. If x hat is not necessarily linear, if x hat is an arbitrary function of y bar, right, can be a if it is a non-linear, if it can be linear or non-linear, then it becomes the MMSE estimator, simply the minimum mean squared error estimator, that is the best estimate x hat such that expected value of norm x hat minus x bar square is minimized. If x hat is a general, right, is the best estimator amongst all estimators, then it becomes the MMSE estimator. If it is best only among the class of linear estimators, it becomes the LMMSE estimator, the linear minimum mean squared error estimator. And as I have already said, the linear MMSE estimator is frequently used in practice because it can be determined relatively easily, especially when the model, right, when the input output model is linear, as we are going to see shortly, right, as we are going to see as we go through these modules, we are going to see how to determine the linear minimum mean squared error estimator. Okay. Now, the general principle of linear minimum mean squared error or the general linear minimum mean squared error estimate can be found as follows. So, we want to consider this quantity expected value of norm of x hat minus x bar square. So, we have this quantity and I am going to use the property here that which we well know, norm x bar square for real vectors, this is simply x bar transpose x bar, which can also be written as trace of x bar transpose, where trace of any matrix A is simply the sum of the diagonal elements for an n cross n matrix A. Trace is denotes the sum of the diagonal elements, right. So, this I think all of you should be familiar. So, trace denotes the sum of the diagonal. So, trace denotes the sum of the diagonal elements of a square matrix. So, I can write a norm of x bar square as x bar transpose x bar, which is also equal to trace of x bar transpose. Alright, this is an interesting property. If you are not familiar with it, you can just quickly check it, because if you look at x bar transpose, the diagonal elements will be x1 square, x2 square, so on, xn square. And this is for a real vector, and you can similarly extend it to a complex vector. In that case, you will simply write x bar Hermitian x bar or trace of x bar Hermitian. Alright. And this is essentially equal to, therefore, I can write this as expected value of, let me just write this as first x bar minus x hat norm square, which now substitute the expression for x hat. Remember, it is a linear estimator. So, this becomes x bar minus c y bar norm square, which is expected value of trace of, now let us bring in the trace. Okay. So, trace of x bar minus c y bar times x bar minus c y bar transpose, and basically close the brackets. And we are using c y bar because remember we have x hat is equal to c y bar. This is a linear estimator, and from here we can expand this thing, which is essentially you make this as follows: expected value of trace x bar minus c y bar, x bar minus c y bar times x bar transpose minus y bar transpose c transpose, which if you expand this term by term, this is going to be equal to expected value of the trace of x bar transpose minus c y bar x bar transpose minus x bar y bar transpose c transpose plus y bar transpose plus c y bar transpose c transpose, and close the brackets. And now we are going to do a standard trick, which is essentially to interchange whenever we have the second order statistics, we can interchange the trace and the expectation. So, trace of expectation is equal to expected value of the trace, right. So, I am going to use the property expected value of the trace of a matrix, because trace is a linear at the end of the day, equal trace of expected value of A. This is possible because trace is a linear operator, right. Trace of A plus B equals trace A plus trace B and so on, because trace is a linear and therefore, now this becomes very interesting. Now, when you say take the trace inside, so this becomes trace of expected value of, writing exactly the same thing, x bar transpose minus c y bar x bar transpose minus x bar y bar transpose c transpose plus c y bar transpose c transpose, which now if you take the expected value of the individual terms, this becomes trace of expected value of x bar transpose minus c expected value of y bar x bar transpose, because C is a constant matrix, minus x bar expected value of C transpose plus C expected value of y bar transpose C transpose. Now, this is essentially, if you look at this you can see this is equal to R x x, expected value of y bar x bar transpose, this is R y x, this is essentially R x y, and this is essentially R y y. So, essentially basically you can simplify this as trace of, substituting these quantities, this becomes trace of R x x minus C times R y x plus R x y into C transpose plus C R y y into C transpose. This is essentially the succinct expression that you get in terms of the various covariances, that is you have R x x, R y y, and also importantly note the cross covariances R x y, R y x. Okay. So, these are the covariances. So, this expression involves the covariances, all the second order statistics, right, and the cross covariances. Imply this involves the covariances and the cross covariances. Okay. And therefore, now I can further write this as the following. I can simplify this as, so trace R x x minus C R y x plus R x y C plus C R y y C transpose, and I will add and subtract terms. I will add and subtract terms. We will see the need for this later. R x y R y y inverse R y x and subtract this term R x y R y y inverse. So, I will add and subtract these terms, and now I have to minimize this whole quantity to achieve the LMMSE estimator. To achieve LMMSE, one has to minimize the above quantity. Alright. So, essentially we have now set down the quantity, that is we can call this as the mean squared error, right. So, essentially what we have simplified so far is expected value of norm x hat minus x bar square, where x hat is a linear estimator. So, this is basically the mean squared error as a function of C, right. So, this is the what you call as the mean squared error, MSE. And this is basically a function of C. So, this MSE is equal to, this is basically a function of the matrix C. Now, if I minimize this function of C, then that gives me the LMMSE estimator. If I minimize this as a function of the C, that gives me the linear minimum mean square error estimator. All right. So, let us carry out this simplification, because this is going to take a little bit of work. So, let us carry out the simplification in the next module, and then we will wrap up and we will look at the intuition behind this principle of LMMSE estimation. All right. Thank you very much.